So I was the reporter for the jet engine cycle. Once again, we all know there's a lot of data, a lot of number crunching in here, so I'm going to try to kind of focus on the pertinent information, stuff that you can kind of grasp and get your head around. So obviously we have the jet engine. So this is actually a turbojet. So the way this works is that the fuel burned in this back portion generates high pressure, and obviously it's going to exhaust. That spins this. It's kind of like, you could think of it as like the fans on like a wind turbine. That spinning then spins the impeller, which is what pulls more air in. So it's kind of like a self-fueling, self-sustaining process. So in this lab, we have the compression, the combustion, high pressure exit, which gives the thrust. So we all know the basics of how this thing works. And we have the thermodynamics of it. So obviously ours is way less than isotropic. Kerosene is not the ideal fuel. It's pretty good. And also this is a very old engine. So they said, the guy in the lab said that they've made lots of changes to this as the company's grown. So this is our raw data. So this is temperatures taken in several different places and pressures taken at those same places, before, after combustion, some during, all at different RPMs, as close to kind of increments of 5 is awesome. 5,000 RPMs, I mean, steps. So we're going to use this data to find the mass flow rate, the thrust, fraction of fuel burned in various different places, which we've all seen by now is tricky. The compression and the turbine work, and the isotropic coefficient. So there are a lot of formulas. I've only included kind of the basics. We use these, manipulate these, and then we find all of the little ones in between that we need to find the actual values that we're looking for: exit velocity, mass flow rate, and that stuff. So there was a lot of calculations. I had a lot of help from people who've done the lab in the past very much. And even with that, it was a very big pain. There's lots of data, lots of things in between to calculate, lots of things to go wrong. Luckily, my data looks pretty good. So our measured thrust is exactly how you would expect. It goes way up after about 65,000 RPM. Mass flow rate, so interpreting the mass flow rate graph is a little bit counterintuitive. You would think that it should look the same as the measured thrust. The reason it doesn't is because as the speed goes up, it reaches a point where the pressure is so low because the velocity of the air is so fast. The density of the air is also low, so you get a lower mass flow rate. If there was a volumetric flow rate, it would look very much like the measured thrust. The efficiency of the compressor is actually pretty good. It's kind of on par. I got a decent efficiency. I looked up the efficiency of this is on the order of 54%. Given that this is an old compressor, it's probably dirty. Probably needs to be cleaned, and kerosene is not the ideal fuel. This is a pretty good ballpark. And the calculated thrust doesn't exactly resemble the measured thrust, but obviously this is not an isotropic process, and some of those differences can be attributed to that. Now, fraction of fuel burn. I intentionally left out fraction of fuel burn in the nozzle because there were errors in it. I had the same problem that Rebecca did. I got negative values. Those negative values probably came from the fact that that fraction of fuel is calculated by doing 100% minus these two fractions, which is where those negatives came from. These two, which would indicate that these two fractions are a bit high. An overestimate here could have been caused by many things. We'll discuss that in the conclusion. So we have the work done by the compression, the work done by the turbine. Again, these are exactly what you would expect. The more RPMs, the more fuel, the more work gets done. Now, comparing these to what other groups had, all of the red lines are our data from our run. All the blue lines are mean values from other people's runs. I think I used the same runs Katie used, and I think she used like 5 or 6 different groups. So it's a lot of data. It's a lot of values. So the on this slide, all of our data is pretty consistent. There's nothing really that odd that can't be easily explained. The compressor efficiency for ours was a little bit high. That could have been due to really many things. I would assume that if you run this thing over the course of a day, the components get hot and you get a cleaner burn, which might be why ours was a little bit higher. Our lab was later in the day. Maybe the components were still a bit hot from other people's labs. Who knows? fraction fuel burn. Now these actually get a much, you get a much more cleaner line than our fraction of fuel burn. And that's probably because the fraction of fuel burn was the most kind of, it was a very optimistic calculation. It's very hard to calculate that. So obviously the mean data would give a much better representation of that than just the huge variations over one run. And then again, the compressor work and the turbine work are similar. The turbine work is possibly the most different graph, with the exception of fuel burn fractions. And again, that could be my calculation error. And it seems that our turbine work is a little bit off, because it seems like it should go a little bit more upward. Oh, wait. Oh, yeah. I don't know. I did the slight opposite. So in this case, the red line is the mean value, because our line is the blue line, which went up in the same way the compressor work did. So why the mean value stays up there, I'm not exactly certain. Again, there are lots of calculations, lots of room for error. So the conclusion. So our measurement devices, the thermocouples are old, and we already had to completely scrap the RPM reading for all of the runs because the computer is not sophisticated enough to do a nonlinear offset for a value. The isotropic assumption, again, is going to be very off base, especially if you look back at this graph. There's a very large difference on the entire right-hand side of the graph, all the way through the burn cycle, which is with 3, 4, and 5. So the isotropic assumption is going to lead to a lot of errors. Also, it assumes complete fuel burn, which is not at all true. Kerosene burns a little slower than regular jet fuel, even though it is using jet fuel. The octane ratings are different. I'm not exactly sure exactly what they are, but I remember the kerosene with some additives that increases its burn rate is what really kind of grade A jet fuel is. So not a complete fuel burn at all. In fact, during startup and kind of giving it flour, you can see the fuel burning outside the nozzle, taking into account any calculations. So the lab also requested T4 and T5 comparison. So T4 is located right at kind of the inside of the combustion chamber. T5 is located at the exit. So on the average, T5 was slightly lower than T4. My assumption, my guess, my best educated guess was that was because the converging nozzle is going to speed the air up as it leaves. As the air speeds up, the pressure is going to go down. So the pressure is going to go down, and the temperature is also going to go down. And you're also getting away from the hotter components of the engine, and the air is allowed to cool a little bit. And because the T5 was outside the nozzle, you do get some kind of, you get some, I don't know what the technical term is for this. Basically, the exhaust is going to suck in air from the outside, and it's going to mix. So you get a little bit of a cooler temperature.